Today we're going over axiom number 6 of ZFC set theory, which is called the axiom of the power set. It says that for any set A, there exists a set B such that for all x, x is an element of B if and only if x is a subset of A. In other words, for any set A, there exists a B whose members are precisely the subsets of A. In layman's terms, if the set A exists, then the set of all subsets of A exists as well. It should also be noted that some books give a weaker version of the power set axiom. The only difference is that the weaker version says that there exists a set B containing all subsets of A without specifying whether or not it might contain some other junk as well. However, if the set B exists, then we can form the set of things in B which happen to be subsets of A. We know this set must exist by the axiom schema of separation. And since if you're a subset of A, then you're in B anyway, well, then this is just going to be the same as this. So just like with the axioms of pairing and union, the weaker version implies the stronger version. I'm going to stick with the stronger version, however, because I think it's more intuitive. So definition, if A is a set, we define the power set of A to be this set, the set of all subsets of A. Let's see an example of that. For example, suppose A, B, and C are distinct sets. What's the power set of this triple going to be? In other words, what is the set of subsets of this guy? Well, here are all the subsets. You can check that each of these guys is a subset of this guy. And conversely, it's easy to see, although it's a little bit tedious to do it formally, that if you're a subset of this guy, then you have to be one of these set. There's only 8 possibilities if you proceed by cases. So therefore, these are precisely the subsets of this set. Therefore, this is the power set. It's the set of all subsets. As an informal note, notice that when we take the power set of a set consisting of 3 elements, the power set has 2 to the power of 3 elements. That's where we get the name power set. Let's do another example. What's the power set of the empty set going to be? Well, we have to ask ourselves, what are the subsets of the empty set? Well, we know that the empty set is a subset of itself. And likewise, we know that the empty set is the only subset of the empty set. Why is that? We recall 2 sets are equal if and only if they're both subsets of each other. So if you have some other set A, which is a subset of the empty set, well then since the empty set's a subset of anything, then the only conclusion is A has to equal the empty set. So the empty set is the only subset of this guy. So therefore, the power set of this guy is the set of all subsets. Since there's only one subset, it's just this. All right, so now let's prove some basic properties of the power set. Well, for one thing, power sets always contain the empty set as well as the underlying set. Why is this true? Well, saying the empty set belongs to the power set of S is just the same as saying the empty set is a subset of S, which is true because the subset is a subset of any set. Likewise, this part right here is just saying that S is a subset of this guy, namely S. Since any set is obviously a subset of itself, this has to be true. That concludes the proof. Our next theorem tells us that power sets are closed under basic operations. So if A and B are both in the power set, then so is the union of A and B, as well as their intersection, as well as their difference, as well as their symmetric difference. Why is that true? We'll assume A and B are both in the power set. That's the same as saying that A and B are both subsets of S. Now, by a theorem we proved in lecture 1.8, if A and B are both subsets of the same set, then so is their union. So since A union B is a subset of S, that verifies A union B is in the power set. Now, what about A intersection B? Well, A intersection B is a subset of A union B, right? Because whenever you're an A and B, you're an A or B. But now by transitivity, this has to be a subset of this, which means that this has to be in the power set of S. So this is true as well. Likewise, the difference of A and B is a subset of the union because this is the set of things that are in A but not in B. Okay, well, if you're in A but not in B, you have to be in at least one of A or B. So again, by transitivity, this has to be a subset of S, and therefore this has to be an element of the power set of S. So this is true. And finally, the symmetric difference has to be a subset of the union because this is the set of things that are in exactly one of A or B. Well, if you're in exactly one of A or B, then you're in at least one of A or B. So every element of this set is also a member of this set. So therefore, by transitivity, this has to be a subset of S, and so therefore this has to be in the power set of S. And that concludes the proof. So we see that power sets are closed under unions, intersections, etc. However, these are binary unions. What about arbitrary unions? It turns out they are closed under arbitrary unions as well. Let's prove it. This next theorem tells us power sets are closed under arbitrary unions. So if you have some subcollection C of the power set of S, then if you take the union, it will belong in the power set. Let's prove it. Assume this is true. We want to show that this guy is in the power set of S. Another way to word that is that we want to show union C is a subset of S. How do we do it? Well, to show subsets, we just got to show that every element of this guy is also an element of this guy. So let X be an element of this guy. We want to show that X is an element of this guy. Well, this part right here is the same as saying X is the member of at least some member of C. Now, here's the thing. C is a subset of the power set of S, right? Power set of S is just the set of subsets of S. So therefore, C is some kind of set consisting of subsets of S, although it may not include every single subset of S. In other words, this tells us that all members of C have to be subsets of S. Well, since X belongs to some member of C and all members of C are subsets of S, then that means X has to belong to some subset of S. So that means X is a member of some subset of S. And so since X is a member of some subset of S, X must be a member of S itself. That concludes the proof. There's a similar theorem which tells us that power sets are also closed under arbitrary intersections. Although for the intersection version, we also need an extra assumption that this set is non-empty, since the arbitrary intersection of the empty set is undefined. Let's prove this. All right, so suppose the hypothesis is true. We want to show this. In other words, we want to show that this guy is a subset of S. In order to prove this, our strategy is going to be to assume we have some X in this, and then our goal is to prove that X has to be a member of this. Well, saying that X is in the intersection is the same as saying that X has to be in every member of C. Now, since C is a subset of the power set of S, that means C is some subcollection of subsets of S. So therefore, every member of C has to be a subset of S. Now, since X is in every member of C, and since C has at least one member because it's not empty, and since all members of C have to be subsets of S, then it follows that X has to be the member of some subset of S. So since X is a member of some subset of S, X has to be a member of S itself. And this concludes the proof. Now here's a little exercise for you. If you take the arbitrary union of a power set, what's that the same as? Pause the video and think about it. Okay, ready for the answer? It turns out if you take the union of a power set, you just get the underlying set itself. Why is that? Well, if X is in this guy, what's that the same as saying? Saying X is a member of this guy is the same as saying that X has to be a member of at least some member of this guy. But now the members of the power set are precisely the subsets of S. So saying X belongs to at least some member of the power set is the same as saying X belongs to at least some subset of S. And now this is the same as saying that X has to belong to S itself. Why is that? Well, because if X belongs to some subset of S, then it has to belong to S itself. But the converse direction is also true, because if you're in S, well, then you have to be in some subset of S, right? Because we know that S is a subset of S. So if you're in S, then technically you're in at least some subset of S. Okay, so we've shown that this set and this set have exactly the same elements, so they must be equal. Here's another exercise for you. What's the intersection of a power set going to be? Pause the video and think about it. Well, it turns out it's just going to be the empty set itself. Now, in dealing with arbitrary intersections, we have to be careful that this guy's not empty, otherwise it's undefined. However, in our case, we're safe because we know that this guy has to not be empty because it contains at least something. Remember, the power set always, always, always contains the empty set, as we proved earlier. All right, so you want to show that this guy is the empty set, right? How can we do that? Well, towards a contradiction, assume this guy is not empty. Well, then if it's not empty, it has to have at least some element. We'll call it X. So that means X has to be in every member of the power set, right? But here's the thing, the empty set is a member of the power set. So since X has to be a member of every single member of the power set, that means X also has to be a member of the empty set. And that's impossible, so we get a contradiction. So therefore, this set must be empty after all. The next theorem is called monotonicity. It says that if A is a subset of B, we can take the power set of both sides, and it's still true. And actually, this pattern, which shows up in many places in set theory and is called monotonicity, the word monotonicity actually refers to the forward direction. However, for power sets, we can do even better. It turns out for power sets, it's an if and only if. So let's prove it, and we'll prove the forward direction first. Assume this is true. Assume A is a subset of B. And what do we want to show? We want to show that this is true. Now, to show that it's a subset, we just got to show that anything that's a member of the first set also has to be a member of the second set. But now being in the power set of A is logically equivalent to being a subset of A, and likewise being in the power set of B is logically equivalent to being a subset of B. So we want to show that all subsets of A also have to be subsets of B. But here's the thing, we know that whenever you're a subset of A, well, since A is also a subset of B, and since subset is transitive, that means whenever X is a subset of A, X has to be a subset of B as well. So this is true. All right, so we proved that whenever this is true, this has to be true as well. Now let's prove the converse direction. Assume this is true. Assume power set of A is a subset of the power set of B. Now, since this is the collection of all subsets of A, and this is the collection of all subsets of B, then the fact that we have this means that every subset of A also has to be a subset of B. Now, A is a subset of itself, right? So since every subset of A has to also be a subset of B, we must have that A is a subset of B. All right, so when we prove that whenever this is true, this has to be true as well. And that finishes the proof. Here's another cool theorem. It says that whenever you have the power set of an intersection, you can split it out like this. Now, why is this true? Well, if X is in this set, what's that the same as? Saying X is in the power set is the same as saying X is a subset of this set, right? But now there's a theorem we proved in lecture 1.8, which said that if you're a subset of an intersection, if and only if you're a subset of both of these sets individually. And saying you're a subset of A is the same as saying you're in the power set of A, and saying you're a subset of B is the same as saying you're in the power set of B. And now saying you're in this set and you're in this set is the same as saying you're in the intersection of those two sets. Since these two sets have the exact same elements, they must be equal. Now here's a question. We proved this cool property about intersections and power sets, but what about for unions? If I change all those intersections to unions, is this still true? And the answer is no, at least not in general. For counterexamples, suppose A and B are both singletons containing just one element each, where both of these are distinct. If you want to, you could take A to be the empty set and B to be the set containing the empty set, for example. Well, in that case, A union B is going to have two elements, namely this guy and this guy. So it's going to be A, comma, B. What's the power set of this guy going to be? Well, it's just going to have four things: the empty set, the singleton containing A, the singleton containing B, and finally, this set. Okay. However, the power set of this set is only going to contain two things. It's going to contain the empty set as well as the singleton A. Likewise, if you take the power set of B, well, B only has two subsets, namely the empty set as well as the singleton containing B. Now, what happens if you take the union of these two sets? Well, it's the set of things that are in at least one of them, right? So in all, there's three different things. There's the empty set, there's the singleton containing A, and there's the singleton containing B. But look, these two sets are not equal. This one contains a pair with two distinct elements. The other one does not. So therefore, the moral of the story is these guys are not the same in general. Notice, however, this guy happened to be a subset of this guy, right? Because everything that's in this is also in this. It turns out that is a theorem. So it turns out this guy always is a subset of this guy, even though equality is not necessarily true in general. Let's prove this. All right, so we want to show that everything that's in this guy is also in this guy. Now, saying X is in the union is logically equivalent to saying X is in the first guy or X is in the second guy. But now all three of these statements here are really subset statements in disguise. So we can rewrite it like this. So now we just got to show that if you're a subset of at least one of A or B, then you have to be a subset of the union. Well, here's the thing. If X is a subset of A, well, we know A is a subset of A union B, right? So by transitivity, then X has to be a subset of A union B. Likewise, if X is a subset of B, well, B is a subset of A union B, right? So again, by transitivity, in that case, X has to be a subset of A union B. So if at least one of these is true, X has to be a subset of A union B. So this is true. And that concludes the proof. Here's a summary of the theorems we proved today if you want to add them to your notes. All right, so we're almost done with the Z axioms. 6 down, 1 to go. Stay tuned for the next lecture in which we'll go over the final Z axiom, the axiom of infinity.